Good evening, class. I am Mohit, and this is assignment number 10 from Electronic Theory of Solid course, which is offered by NPTEL. And in this assignment number 10, I'll be solving the problem which are based on the superconductivity and the Ising Hamiltonian. These are the concepts which has been discussed in the class, and through this assignment solution problem, I'll be addressing the questions, which are the 10 of such questions, which will help you understand and develop the clarity of the concept which has been discussed in the class. It will also give you a view on how to approach such kind of problems, the numericals. And having said that, I'll start with the question number 1, which says that for the nearest neighbor Ising Hamiltonian in a magnetic field H, here H, small h is a magnetic field, and capital H is symbol of Hamiltonian operator, Hamiltonian operator. So H Ising here, H Ising is means the Hamiltonian with of Ising Hamiltonian. J SI. So SI's are spin quantum numbers basically. H is magnetic field and then SI is the spin. And where SI and SJ can take value plus minus 1, which then if that is true, then which of the following is the wrong statement? So the four statements are given 1, 2, 3 and 4, out of which we have to figure out which of them is wrong and which all of these is right. And based on this, this question will be addressed. So having said that, let's approach the first option, which says that summation over Si is equals to plus minus 1 phi, which is a function of Si, is equals to summation over Si is equal to plus minus 1 phi of minus Si at h is equals to 0 for any function phi which depends on the set of spin Si. Okay, phi is any function. The shape and the form of the function is not given, but phi is any function which depends on the spin, and we have to solve it and then we'll come to know. So let me write the phi Si. So if I start writing this one, I will write S1 S2 is equals to plus minus 1. That's what is given. Phi Si is equals to summation over Si S2 is equals to plus minus 1 phi S1 S2. Let's write this one. So if let's expand this one, so it can be written as, so I'll be writing plus 1, all the four combination basically. So phi plus 1 plus 1, then since they are all in summation, so phi plus 1 minus 1 plus phi minus 1 plus 1 plus phi minus 1 minus 1. So this is our equation number 1. Now equation number 2. So Si has to flip the sign, so minus S1 minus S2 can take value plus minus 1. Phi Si is equals to summation of Si S2 is equals to minus plus 1 phi S1 S2, or better, yeah. Now let's substitute the values. Phi minus 1 plus phi minus 1 plus 1 plus phi plus 1 minus 1 plus phi plus 1 plus 1. Compare equation 1 and 2. This gives you that summation over all si's equals to plus minus 1 phi si is equals to summation over si is equals to plus minus 1 phi minus of si. So this is true. This statement is true. This statement is true. And the question asks us about the wrong statement. So definitely this is not a wrong statement. Now the Hamiltonian has a symmetry H Hamiltonian, which is a function of small h, that is the magnetic field, J angular momentum, SI spin angular momentum is equals to H minus H J minus SI. Let's see it. So let's first write the H. H is what? Minus J IJ SI SJ minus H summation over I's SI's. Yeah. Now option says, what do options say? It says that H is a function of small h, j, and s I is equals to h is equals to minus h j minus s. Okay. Now so this is already a function of hjsi, so I will just write it here. This h is already a function of, copy and then paste. Now let me call this equation number 3. This implies comparing 3 and 4, calculating let's say this modifying equation 3, rewriting equation number 3. H H J S I's equals to minus J I J. I can write it like minus S I and minus S J because that will cancel the sign, and minus H summation over I S I. or I can write it better. This is minus H times minus Si. So this translates into H J Si equals to minus J. So I can write this part of the Hamiltonian. If I replace Si with minus Si, H with minus H, and J remains J. So I can write this part as H minus H J and minus of Si. And look, this is exactly this is exactly equation number 4. That is option 2 is true. So option number 2 is also true. Now moving on to the third option, which is triangular lattice doesn't have the sublattice symmetry. That is symmetry between j greater than 0 and j less than 0. That's what it says. So let's just solve it. So option number 3. It says that the triangular lattice doesn't have the sublattice symmetry. That is symmetry between ferromagnetic and antiferromagnetic. So a triangular lattice is what? A lattice which is like this. This is a triangular lattice. So a triangular lattice, let me write it, a triangular lattice. Triangular lattice. So a triangular lattice doesn't have the sublattice symmetry. So Ising model for j greater than 0 will have all spins up pointing in the same direction at 0 temperature. And okay, so Ising model on a triangular lattice with j greater than 0 will have all spins floating. Better word will be pointing in the same direction at t equal to 0, and in j less than 0, in analogy with the cubic case, the spin should point up and down alternatively. Which is not possible, right? In triangular lattice, this is not possible on a triangular, and this is not possible. That's what gives rise to the frustrated antiferromagnet kind of thing. Possible on a triangular lattice because of geometry. And for example, what does it mean? See, for ferromagnet kind of thing, all the spins can align in one direction. That is okay. This is ferromagnetic. But in case of antiferromagnet, spin has to be alternatively, if this is up, this has to be down. Now, what about this one? If this can be either up, this side can be either up or down. If it becomes up, the side which is adjacent, let me call this A, B, and C, A, B, and C. So this here, up and down, both possible. And this is called frustration. So the triangular lattice doesn't have the sublattice symmetry. It does not have the sublattice symmetry. Okay. So this is also true because that's what the statement says, that the triangular lattice doesn't have the sublattice symmetry. That is symmetry between j greater than 0 and j less than 0. It doesn't have. Now comes the option number. This means option number 3 is right. True, basically. This implies option number 3 is also true. Now coming on to the next option, which is option number 4. What does it say? It says that zero field energy zero field energy has the property F, which is the free energy. So H is 0, J and T. T is the temperature. Where T is the temperature. So let's just do it. So let me write the option number 4. What the option number 4 says, otherwise I'll forget. Zero field energy has the property F 0 J T is equals to F is not equals to F 0 minus J T. T is equals to temperature. Now let's just write it and then we'll come to know. So you can write the zero field partition function, and if the partition functions are same, then the zero field energy will be same. If the partition functions are different, then the resultant uh, zero field energy will also be different. So let's just write it. So the zero field partition function means h is equals to 0. So we write as a j z 0 minus j and t. We all know how do we write the partition function. So si is equals to plus minus 1. That's there in the Hamiltonian, exponential minus beta. So beta is 1 by kbt. K is Boltzmann constant. H 0 minus j and si is. So we can write it like SIA is equals to plus minus 1 and summation over SIB is equals to plus minus 1 exponential of minus beta h 0 minus j SIA SIB, since two spins are possible, so both of them, and then let's just do it. SIA is equals to plus minus 1 SIB is equals to plus minus 1 exponential of minus beta h 0 j SI and SIP. And this implies Z 0 j t. So what does it says? That free energy, if the partition functions are same for this, then free energy will also be same, 0 jt equals to F 0 minus jt. Yeah, if they are same, but option says that they are not same. In that case, this implies option number 4 given. Option number 4 is incorrect. So since the question is asking the wrong statement, so the option number 4 becomes the answer to this question. Yeah. So this is question number 1. If you have any doubt or question, you can ask me in the comment box. I'll be happy to address it. Yeah. So if that's not the case, then you can also think it like in the term of the another way which you can think is j becoming negative is, you can think like flipping the spin kind of thing, total spin. So option number 4 can also be treated like, can also be treated like you have triangular lattice, and in the triangular lattice for j greater than 0, you say that all the spins are up. So I'm drawing them like this, and for j less than 0, what will happen? All the spins will flip in the other direction. Since magnetic field is 0, since H is 0, what will this imply? If you consider the system A and the system B, energy corresponding to A and B will be same because nothing differs them. Just the orientation of the spin. Either it can be up, all are up, or all are down. So the energy will not differ if the applied magnetic field is 0. So energy corresponding to A and B will be same. This will also imply that free energy 0 J T is equals to free energy 0 minus J T, and this is the second method which we can prove. So first we proved it with this method of writing the partition functions for both j is greater than 0 or j less than 0, this method. The other way, intuitive thing, you can do it like this. You can draw the diagram and can flip the spin for j greater than 0 or j less than 0. This will also give you the answer for this problem. So with the two of the methods, we have seen how to approach and solve this problem. Now, having said that, let's move on to the question number 2, which is lead is 7.26 Kelvin. The critical magnetic field at 0 Kelvin is given 64 into 10 power 3 ampere meter inverse. The critical field at 5 Kelvin is asked. So we know the relation between, as it has also been discussed in the class, I will write it again. So the critical temperature, let me write whatever information we have. Critical temperature Tc given is 7.26 Kelvin. Critical magnetic field given is, so critical magnetic field is denoted by Hc, that is 64 into 10 power 3 ampere meter inverse. Then we know the relation between the critical field, the relation between critical field and the temperature is Hc is equals to H0, that is your critical magnetic field, which is given H0 at T equal to 0 Kelvin, 1 minus T over Tc. Tc is your critical temperature, below which your material is superconducting, above which your material won't be a superconductor. So that's the critical temperature. So if all the information is given, so Hc is equals to H naught. Let me write H naught is 64 into 10 power 3 times 1 minus the temperature for which they are asking is 5 Kelvin. So temperature is 5 Kelvin by Tc is 7.26 Kelvin square. So if I solve this thing, 5 by 7.26 is 5 divided by 7.26 is 0.6887, 0.6887. So the square will be Hc is equals to 64 into 10 power 3 times 1 minus 0.4743. So subtract the 1 and multiply the 64 with it, you will get 33.64. So critical field at this given temperature will be 33.64 into 10 power 3 PM meter inverse. So here the answer which goes here is 33.64. So answer up to one decimal they are asking, so 33.6 is the correct answer for this problem. So this is the question number 2. If you have any doubt, question, you can ask me in the class or in the comment box. I'll be happy to address it. Okay. If you don't have any question, let's move on to the problem number 3, which is which of the following is true for a superconducting state? A superconductor is the superconducting state exhibit perfect diamagnetism. Yep. So let's just address this problem one by one. So which of the following is true for a superconducting state? So a superconductor is the superconducting state, temperature is less than Tc, that is it is in the superconducting state, and it exhibits perfect diamagnetism, that is chi is equals to -1. What is chi? Chi, option 1, let me write option 1. Chi magnetization equal to chi times H, and for perfect superconductor, if it's a superconductor, then from the Meissner effect, a superconductor expels the magnetic field, and in perfect diamagnetism correspond to susceptibility of chi equals to -1, because it can generate whatever amount of the current which is required to expel the magnetic field. And in that case, from the Meissner effect, from the Meissner effect, superconductor superconductor expels the magnetic field, and magnetic susceptibility is chi equals to -1. This means that internal magnetic field is zero, because magnetic field cannot exist inside the superconductor. Yes. The entropy in a superconducting state is higher than in normal state. So this is true. Option 1. Option 2. The entropy in a superconducting state is higher than in normal state. This statement is false. Why? Because superconducting state is more ordered than the normal state. Superconducting state is more ordered than the normal state. And this implies less entropy. So this statement is, option 2 is false. Option number 3 is that the critical temperature Tc goes as 1 by m, where m is the mass of an isotope. Okay, so option 3. So this is isotope effect. And this has been already discussed in the class, that Tc goes as 1 by root m, not 1 by m. This implies false. The relative permeability mu is equals to 1. Okay, let's just see it, how chi and mu are related, and then we'll be able to address this one. So option number 4, we know that mu r is equals to 1 plus chi, right? And For superconductor, since we have already seen in option number 1, chi is equals to -1, that is perfect diamagnetism. This will implies mu r is equals to 1 minus 1, that will be mu r is 0. So the permeability of a superconductor is 0. So this statement also becomes that mu r is equals to 1 also becomes false. So the correct option here is the answer number of given option is correct option is 1. Now moving on to the problem number 4. And if you wonder where this relation come from, so you know that the derivation starts with B, that is the magnetic flux density is equals to mu naught H plus M, and then you write M is equals to chi times H. This gives you B is equals to mu naught H and 1 plus chi, and this quantity mu naught H 1 plus chi you write as mu H, and your mu by mu naught is equals to mu R is equals to 1 plus chi. So this is where this relation comes, where H is the magnetic field strength and M is the magnetization and B is the magnetic flux density. Okay, just in case if you wonder like where this relation comes from, this can be easily derived. Okay, now moving on to the problem number 4, which says that in a superconducting state, resistivity, which is rho, E is electric field, B is the magnetic field. Okay. So in superconductor, we know that there is no dissipation. If there is no dissipation in superconductor, T less than Tc, no energy dissipation. This implies rho is equals to 0, because resistance is what? It is the dissipation. One second. Sorry. So rho is equals to 0. Now, in superconductor, no electric field, steady state electric field can be there. No steady state electric field. Why? Because a current can flow without any voltage drop. Now option number 3 is the magnetic field. We know that superconductor is a perfect diamagnetic material. Material. Magnetic field is expelled from the bulk such that the inside the magnetic field of the superconductor is zero. And we know that this is Meissner effect. It implies P is equals to 0 inside the superconductor. Therefore, the correct option here is option number 3. Now moving on to the next problem, which is the critical temperature of mercury with isotope mass 200 mu is 5 Kelvin. The critical temperature of its mass changes to 205. Okay, we answer 5. This is an easy problem to solve. So we know that critical temperature Tc goes as 1 by root m. So Tc1 will go as m1. Tc2 will go as root m2. So Tc1 by Tc2 is equals to root m2 over m1. Now if we want to extract the Tc1, it will be Tc2 times root m2 by m1. Tc1 will be Tc2 already given is 5, m2 given is 200, m1 is 205. So 200 divided by 205 will be 0.9756, and square root of that, square root of 200 divided by 205 is nothing but 0.9877. 5 into 0.9877. So if I multiply this number by 5, the option which I will get is 4.9386. So the TC1, since the question is asking up to the second decimal, so 4.94 Kelvin. So the correct option here is 4.94 Kelvin. Okay. So if you have any question or doubt, you can ask me in the comment section. I'll be happy to address it. Okay. If there is no question, then let's move on to the next problem, which is which of the following is true about the Mermin-Wigner theorem regarding the symmetry of the order parameter? So we know that Mermin-Wigner theorem stated the continuous symmetry cannot be spontaneously broken at finite temperature in system with a sufficiently low dimension, that is dimension less than equal to 2. This theorem applies for discrete symmetries. Not it applies for the continuous symmetry, not for the discrete symmetries, and therefore it applies to only continuous symmetry, but not to discrete symmetry. So let me write Mermin Wigner theorem applies to continuous symmetries and not discrete symmetries. Yeah. So if you look at this one, then option 2 is the correct option, that it applies to the continuous symmetry but not to the discrete symmetry. But we will address the other options also. Yeah. So the first option, which says that it applies to both continuous and discrete, no, because it applies to only continuous. It applies to continuous symmetry but not to discrete symmetries. This is true. It applies to discrete symmetry but not to continuous symmetry. This is false. It implies that long range order cannot be sustained in any dimension. No. Theorem says that long range order cannot sustain in D in dimension D less than equal to 2. In 3D it can be possible. In 3D it can be possible. And this is the theorem which predicted that the graphene will not exist, the 2D material will not exist, because the long range order will not be there, and the atoms will fluctuate kind of thing, and they will break apart kind of thing. But in 2004, Kostanov and Andrei Gain, they exploited the graphene and proved that the 2D material can exist with the long range orders also. So that's something interesting. So now, having said that, moving on to the problem number 7, which says that isotope effect in tin. So isotope effect, we know that the temperature will go as inverse of square root of mass. So the following data were obtained for the dependence of the critical temperature in Kelvin of tin on its average atomic mass. So m and Tc's are given. If 1 by root m is on x-axis and Tc is on the y-axis, which of the following is correct? So this x-axis is 1 by root m, and the y-axis is Tc. From the isotope effect, we know Tc goes as 1 by root m. This implies Tc is equals to some constant, slope times 1 by root m. Yeah. And with increasing 1 by root m, this slope is positive. Your Tc will also increase. This implies if I plot the Tc and m, it will go like a linear line with positive slope. This implies option B is correct. Figure B. So if this is correct. Yeah. Now moving on to the problem number 8, which says that which of the following statement regarding superconductor is false. The first option is magnetic field enters in the form of flux inside a type 1 superconductor. This is wrong because the magnetic field flux enters in type 2 superconductors, not in type 1. So this statement is wrong. And so let me write it in detail so that you don't forget whatever I'm saying. Option 1, type 1 superconductor shows a complete Meissner effect. They expel all magnetic fields up to the critical field. And after critical field, the superconductor won't be superconductor. In type 2 superconductor, magnetic field flux enters in the form of quantized vortices. So this statement is option 1 is false. Now option 2, so the London equation is got curl of J is equals to minus P by MC. That's what it is, right? And the J you can write in terms of, in Gaussian unit, J you can write minus NE square A by M. In Gaussian units, J is equals to minus NE square by M times A. So your curl of J basically is minus NE square by M. Curl of A is nothing but the B, so it will be, and then there will be MC kind of thing. So this is also true. London equation is consistent with P minus EA by C is equals to 0. Yes, this is true because the condition reflects that the canonical momentum, which is P of the Cooper pair, cancels the electromagnetic potential EA by C, which lead to the London's equation. So London option 3. Is consistent with P minus EA by C. This is canonical moment of Cooper pair. and this is electromagnetic potential term. Okay. And this is consistent with this one. And the last option, this we have seen in the class also. The London penetration depth is the distance over which an external magnetic field is screened out inside the. That's what definition is. The London penetration depth is, right. So option 4 is also true. This is true. Option 4 is also true. This is correct. Answer to the question is option 1, because the question is asking about the wrong statement. Yeah. Now, moving on to the next problem, which is like, which of the following is false for magnons in ferromagnet? So, it is a collective excitation of the electron spin structure in a crystal lattice. Yeah, so let me introduce the magnons first, then it will become more clear, I think. So, statement 1, I'll say that magnons are quantized spin waves, that is collective excitations of the spin ordering in ferromagnets. They represent the precision about the ordered direction. Precision of spins about the ordered direction, whatever the ordered direction is, because they are in the ferromagnet. This implies option 1 is true, because it is a collective excitation of the electron spin structure in a crystal lattice, that is in the ordered. At long wavelength, the frequency is proportional to k square. This we have discussed in the class also. Option 2. In simple ferromagnet, the magnon dispersion relation at long wavelength omega k goes as dk square, where d is the spin stiffness. Spin stiffness. And k is wave vector. So it goes as k square. So this is also true. At long wavelength, the frequency is proportional to k. So if this is true, then option 3 automatically gets false. Because it goes as omega k proportional to k square, not. Okay, this is fine. So this is false. Magnons are boson and hence follow Bose-Einstein condensate. This is absolutely true. Magnons are bosonic quasi-particle and they obey the Bose-Einstein statistics. This leads to a phenomena like magnon condensation at low temperature. Option 4. Magnons are bosonic quasi-particles and obey Bose-Einstein statistics. Okay, so this is also true. So the correct option for this question is at long wavelength, the frequency is proportional to case, because this is only the false, others are true. And the question is asking about the false for the magnons in ferromagnet. If this is clear, then I will move on to the next problem, which is problem number 10. So the problem says that a superconducting ring carries a steady current in the presence of a magnetic field B normal to the plane of the ring. Which of the followings are incorrect? Again, again, this assignment is more focused on what is incorrect rather than being correct. Okay, so we'll handle this final question also. So what the problem says is you have a ring of superconducting wire. This is the magnetic field, perpendicular magnetic field. Some current is flowing in this wire I. The flux passing through the superconductor is quantized in units of Hc by E. So option 1, the correct unit of flux quantized in a superconductor is Hc by 2E, not Hc by E. And why 2E? Because they are Cooper pair and have a total charge of 2E, not E. So the correct unit of flux quantization in superconductor is Hc by 2E. 2E factor arises from Cooper pairs. So this statement is incorrect or false, because the statement asks about Hc by E. Correct answer is Hc by 2E. The current and the magnetic field in a superconductor are time independent. This is correct because in a superconducting state below the critical temperature, the supercurrent is persistent and does not decay with time. Option 2. In the superconducting state, below Tc, the supercurrent is persistent. Persistent and does not decay with time. And likewise, the magnetic field, if external condition does not change. So this statement is true. Whatever the question says. The current density J and B are related by the equation curl of J is equals to 0, where lambda is a constant. This we have already discussed. That curl of J in this problem, if you see, is minus n e square, the London's equation basically. So let me copy it and I will paste it here. Option 3. Paste. So curl of J is equals to 0 only true if B is equals to 0. So this is false and not in general true. This makes the option number 3 statement false because it says that it is always true. So this is false. Now moving on to the fourth option, the supercurrent does not decay over a very long time. Yes, this is true. This is the feature of the superconductor, that it does not have any resistance, and if there is no resistance, there is no reason why the supercurrent will decay over a very long time. So option number 4, a definitive feature, or if I say a defining feature of superconductivity is the supercurrent is that supercurrent is dissipationless and persists indefinitely. In the absence of external disturbance. So this statement is true. Now the question asked us about which of the following are false. So we have seen that the option number first is false and third is false. So the correct option here is answer number 3. Given options first and third are false. So with this one, this assignment number 10 is concluded. So if you have any question or doubt, you can ask me. I will wait for 10 more minutes in the class. If you have any question or doubt, you ask your question. I'll be happy to address it. So I will wait for the time, given time, and after that, after 10 minutes, I will conclude the class. Okay, if the class don't have any questions, I will conclude this session. That is the assignment number 10. See you class on next Monday with the assignment number 11. Till then, bye bye.